now that we're familiar with rational numbers, it's time to start performing some operations. So that's what this section is about. The I can statement for section 4.3 is I can perform rational number operations without a calculator. So we're going to work on these without a calculator, and a lot of this stuff I'm hoping that you've seen before, that you're somewhat familiar with, but we want to be really good at this, and so a reminder here and a review will I think help. So as a warm-up today, what we're going to do is we're going to complete each one of these count bys up to the equivalent of 1 without looking at your notes preferably. Hopefully you've spotted those patterns in fraction and decimal form, and just can kind of go through and count by fractions or decimals, whatever happens to be. So we're going to start with fifths. Fifths are a very common rational number, so we're going to go 1/5, then 2/5, 3/5, 4/5, and I get to stop at 5/5 because when the numerator is the same as the denominator, that would be the equivalent of 1. Let's do the same thing right here. So we're going to count by 0.2. So this is like counting by 2. So this is going to be 0.2, 0.4, 0.6, 0.8, and it's not 0.1, it's 1.0. So don't mix that up. So that's the equivalent of 1. So it's kind of like we have 20 cents, 40 cents, 60 cents, 80 cents, and then we have $1. So keep that in mind. Now, if we're going to count by eighths, so eighths, this would be 2/8. So that's going to be 1/4. 3/8 doesn't reduce. 4/8 is the same as 1/2. 5/8 doesn't reduce. 6/8 is the same as 3/4. And then 7/8, and then 8/8. Whoops. 8/8 of course would be the equivalent of 1. Stop at the same place there once we get up to 8/8. Okay, let's count by 0.125. So you might remember that these are equivalent. We're counting by eighths, but this time in decimal format. So we're going to go 0.125. So that's going to be 0.250 or 0.25. Then it's going to be 0.375. The next one's going to be a half, so that's going to be 0.5. The next one's going to be 0.625. And again, these take a little time to memorize. 0.75, 0.875, and then of course 1.0. And a couple things that might be helpful is think of this as counting by 125. So this would be 0.250, 250. Another 125 would be 0.375. Whoops, let me write that the right way. Another 125 would be 0.500. So the next one would be 0.625, and then another 125, 0.750, another 125 on top of that. So you can kind of see how we're just counting here, and if we wanted to kind of expand that out, that's what we'd have there. So kind of keep that in mind. It's really good to be able to count by different fractions and decimals, especially if they're those common rational numbers we talked about. Now, going way back, and this is not something that we can forget, let's think about the rules for combining integers. Remember, if they had the same sign, we find the sum, and then we give the answer the same sign as both of those have. So if we're combining, adding or subtracting integers, same sign, find the sum, keep the same sign all the way through. If they have different signs, find the difference and give the answer the sign of the larger one or the bigger one. And remember, when we were saying larger, what we meant is the largest one in absolute value. So those were the rules for combining. And then the rules for multiplying and dividing integers, remember, a positive times a positive was a positive, positive times a negative is negative, negative times positive is negative, and then negative times a negative is positive. And then the rules are the same for division. Remember that negative is the thing that can change it to the opposite sign. So if we've got two of them, it just changes it and then changes it back right where we were to begin with. Okay, well, hopefully you're getting more comfortable with fractions and decimals. The more you work with them and the more you're familiar with those common rational numbers, the better off you're going to be. Well, now we're going to work on performing operations on rational numbers. And we're going to do this without a calculator, as we mentioned earlier. So again, just a reminder, we're talking about rational numbers, and we throw that word around a lot. When somebody says rational numbers, you just need to think, okay, we're dealing with fractions, or at least numbers that can be written as a fraction. So even though you may like decimals more than you like with fractions, if you recognize rational numbers, whether they're in fraction form or decimal form, You may find that the answer is often much easier to find in fraction form. So to kind of illustrate that, I'd like you to take a look at example number 1. So which of the following problems would you rather do? Would you rather do 0.875 minus 0.625, or would you rather do 7/8 minus 5/8? Well, because these already have a common denominator, that's going to be 2/8, so the answer on that one's 1/4. If we were to stack the two of these, 0.625, so that's going to be a 0, that's going to be a 5, and that's going to be a 2. So either way, we get the equivalent rational number, 1/4 in fraction form and 0.25 as a decimal. But let's take a look at this one right here. Would you rather do 0.14857 repeating, or negative 1.42857 repeating, minus 0.428571 repeating, or would you rather do negative 1/7 minus 3/7? These are actually exactly the same problem, just like the two of these were the same problem. So it's much easier to do this one right here. Remember, same sign, we're going to find the sum. So they're definitely going to be sevenths. 1 and 3, that would make 4, and then we keep the same sign. So the answer on that one's 4/7. Definitely easier to do in fraction form there. So all I'm going to do right here is we're just going to go through and we're going to look at each one of these problems and just perform the operation. If it says add, if it says multiply, divide, whatever it happens to be, and it says we're going to find each one without a calculator. And although fractions are a preferred way to write your answer, you can write it as a fraction or as a decimal unless the original problem was written only with fractions. So there's, I think, one on here that has a couple on here maybe that have just fractions, so we definitely want to write the answer as a fraction on that one. So let's take a look at this one right here. If we have negative 3/10 plus 0.5, I would recognize that as 1/2, or let's think of that as 5/10. So this is going to be negative 3/10 plus 5/10. Different signs, we're going to find the difference. Difference is 2. So let's see, the bigger one's positive, so this is going to be positive 2/10, which we'd reduce to 1/5. That would be fine there. Or if we wanted to, we could do this. We could do negative 0.3 plus 0.5, and then we'd have positive 0.2. Same either way. Those are interchangeable. Whichever way you want to do it is fine, but again, it's recognizing those common rational numbers that we talked about. Okay, let's take a look at this one right here. Whenever we have a repeating digit like this, like 0.1, 0.2, 0.3, or something like that, it's going to be a ninth or some equivalent of a ninth. So this is going to be negative 1/9 minus 1/3. I'm going to get a common denominator for that, so that's going to be negative 1/9 minus 3/9. So that's going to be negative 4/9. Make that look a little better there. If we were doing this one's not too bad to do. So we've got these repeating decimals. Okay, and luckily we have the same sign, so we find the sum. So this one wouldn't be too bad to get 0.4 repeating, and it would be negative. So either way there is fine, but I do think it's going to be a lot easier to do in fraction form. Let's take a look at this one right here. 7/8 minus 0.625. If you remembered what this one is a decimal, I'm going to do this in fraction form first. I'm going to do 7/8, and remember this is 5/8. So we end up with 2/8, which is 1/4. So we've got 1/4 for our answer there. If we remember what this is in a decimal format, 0.875 minus well, this should look kind of familiar. This is the one we did up above, so this is going to be 0.250. So 0.25, same thing there. Let's take a look at this one. We could take the time to change this into a decimal. I'm going to do it in fraction form first. So this is going to be, let's see, negative 7/2, and then this is going to be plus, let's see, 5 times 1 is 5 plus 3, so this is going to be 8/5. I'm going to change those into tenths. So let's see, multiply that by 5, so that's going to be 35/10. And double this, so that's going to be 16. So if we do a little subtraction problem, we end up with negative 19/10, and that doesn't reduce at all. If we wrote this as a decimal problem, let's see, that's going to be negative 3.5 plus, got to think about 3/5, that's going to be 0.6, so 1.6. Different signs, find the difference. The difference is 1.9 and the bigger one's negative. Okay, so same answer either way there. Alright, let's keep going here. We've got a decimal times negative 1/2. I am going to think of this as 9/10 times negative 1/2. Now the nice thing about working with fractions, when you're multiplying them, that's actually easier than adding or subtracting, because you just multiply straight across. So I'm going to multiply and get negative 9 on the top and 20 on the bottom. Remember, the bottom can't be negative also, otherwise that would turn the answer to a positive. They don't have anything in common, so they don't reduce, so we're good there. If we were to change this to 0.9 times negative 0.5, positive times the negative is negative, we'd get 4/5, and then we have two decimal places, so we'd get 0.45. Those are equivalent, so you're fine there. Let's see, 2/9 and 0.125, so 2/9. I'm going to stick with doing this in fraction form first, because that would be negative 1/4, and I want to show you a couple things, and this is why fractions turn out to be pretty nice to deal with. First of all, we can do some cross cancellation here. I can cross cancel the 2 with the 4. It's kind of like reducing the problem before we multiply. So 2 goes in here once and 2 goes in here twice. So on the top we have a 1 times a negative 1, so that's a negative 1 on the top, and on the bottom we have a 2 times 9, which is 18. So the answer on this one's going to be negative 1/18. Now if we try to do this in decimal form, that gets to be a bit of a hassle, because remember, if we've got 2/9, we're going to have 0.2222. This is going to go on forever, and then we're going to try and times that by negative 0.25. So doing this in decimal format would be a real pain in the butt. I mean, we can definitely tell that the answer is going to be negative, but other than that, this is going to be just a huge pain. Okay, so let's not do that one. Let's just stick with the answer in fraction format. This one here, oh, and I forgot to point out on D up here, you do need to write the answer this way, because the original problem was written with fractions. So we wouldn't want to write that. We'd want to write that negative 19/10. And again, that's totally okay that it's improper. We're fine with that. This one here, again, we're going to do this one in fraction format. So remember, when we're dividing fractions, we never divide by a fraction. We always flip that second one over and we multiply. So this is negative 6/11. Then we're going to change it to a multiplication problem. I'm going to write the negative 7 on the top and the 6 on the bottom, because then what I can do is, you'll notice that I can do some cross canceling right here. I can do a little bit of simplification first. 6 goes in here once. 6 goes in here once. Negative 1 times negative 7 is 7. And 1 times 11 is 11. And it's that quick. We're done. Now, if we were to take a look at this problem right here, there are, again, a couple different ways that we could do this. Let me just show you. If we were going to do this using decimals, here's what we'd need to do. We'd need to do negative 0.6 divided by 0.375. So that means 0.375 would be on the outside of the box, and negative 0.6 would be on the inside of the box, and then we've got this mess to deal with. That's really not going to be any fun. So let's do this in fraction form, and I'll show you how quickly this works out. This is going to be negative 6/10, which would be negative 3/5. We're going to flip this over and we're going to multiply, so this is going to put an 8 on the top and a 3 on the bottom. Again, we look for cross canceling. We can't cross cancel anything with a 5 and the 8, but I can cross cancel the 3's. That goes in once and that goes in once. So I have a negative 8 on the top and I have a 5 on the bottom. And that's the answer. Much, much quicker. So hopefully you can see, as we've gone through and done these, especially when we're multiplying and dividing, it's way easier to work with these in fraction form than it is to work with them in decimal form. So if you flip the page over, these are not things that we have to do, but these are a couple things that would be good if you kind of kept track of. Good thought questions to make you think about, well, how do these work? So what if we had to do a problem like this? Negative 1.5 divided by 12. So if we were doing this problem, we could do, well, first of all, the answer is going to be negative. Okay, let's figure that out. And then I'd have to do 12, 12 into 1.5, and I'd have to go through and do all of that sort of stuff if I were going to do it in decimal form. If I were going to do it in fraction form, here's what I could do. I could write this down as -3/2, because that's 1.5, and then divide by 12, and I could think of that as a fraction. Well, if I think of that as a fraction, remember, we don't actually divide fractions, we flip the second one over and we multiply, so that's going to be 3/2, and then I'm going to do 1/12. And then I look and I see, well, hey, wait a minute, look, I can do a little bit of cross cancellation. I can't cancel or reduce anything with the 2, but I can do the 3 and the 12. So 3 goes in here once, and 3 goes in here 4 times. So on the top we have a -1 times 1, so that's a -1, so there's our negative answer. And on the bottom we have an 8. So the answer on this problem is -1/8, which is way quicker than doing the problem this way. So that's a good problem right there to kind of keep track of. Think about how we do things with fractions and decimals that are mixed, especially if we're dividing. Fractions generally are going to be the way to go. They're going to make it easier. Next question, and you may or may not know the answer to this, is why do we need a common denominator when we're combining fractions? So if we're adding and subtracting, we've got to get a common denominator. Multiplying and dividing, we don't. So if we need a common denominator, what's the reason for that? Okay, well, let's say we have something like this: 1/4 plus 1/6. 1/4 plus 1/6. Well, let's make this as easy as we can. I'm going to draw a cake, a really long cake, and I'm going to draw 2 of them. Okay, and this one I'm going to divide into fourths. So I'm going to cut it in half and then cut each one of the halves in half. Okay. So this represents the 1/4, okay? And this one I'm going to do in 6, so I'm going to cut that in half, and then I'm going to cut this in thirds, okay? So that's going to give me a 6, 2, 6, 3, 6. There's 4, 6, 5, 6, and 6, 6. Okay, so if I do a 4th plus a 6th, here's the problem we run up against. Question is, how much of this cake do I have? If I had one long cake here and one long cake right here, they're both the same size, and then this one right here, I'd have a 1/4 of it, and here I have a 1/6 of it. What fraction of a cake do I have altogether? Well, the problem with this is these are not the same size pieces, so it's really tough to add them. If you and a sibling were arguing about which piece you had, hey, each of you get one piece of cake, you would want this one right here. You'd want the bigger one. You'd want the one that was a 1/4 of a cake rather than the one that was a 1/6 of a cake. So in order to figure out how much of a cake we have so we can split it up or whatever we're going to do with it, what we have to do is we have to make these the same size piece. So I'll watch and we'll do something kind of clever with this. We're going to take this and we're going to divide this into thirds. So we're going to do that with every single one of these. And we're going to divide each one of these in half. Okay, so you'll notice that as much as possible with my crappy handwriting and drawing and everything, all these lines line up. Every single one of them, okay? They're right on top of each other. So what we have now is we have the same size piece. Well, let's figure out what size piece we have. Well, let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So what we have here is we have 3/12, and here we have 2/12. So what we've done here is we've made them the same size pieces so we can actually add them up and figure out, okay, how much do we have here, and how could we add them up or divide them or whatever we're going to do with them, okay? So getting a common denominator makes the pieces the same size. That's why we get a common denominator. These were not the same size pieces. When we were talking about this piece right here and this piece right here, they were not the same size piece, so we couldn't combine them together. If we get a common denominator, slice the pieces so that they're the same size. Now we can go ahead and combine them. So now we have 3/12 plus 2/12 is equal to 5/12, just short of, and if I were to shade this in, just short of half a cake. So that's why we have to get a common denominator, because it makes the pieces the same size. All right, last question. And again, these are just things that you may or may not be interested in. If you get these, great. If not, no big worry. Next question is, why do we multiply by the reciprocal of the second fraction when dividing fractions? Well, let's say we have something like this. Let's say we have 2/3 divided by, we'll do 1/4. Okay. Well, another way to write this is, since we're taking a fraction and dividing it by a fraction, what we're doing is we're taking 2/3 and we're dividing it by 1/4. Okay, so I've got 2/3 divided by 1/4. It's just a different way of writing the same thing. Well, we don't like denominators that are ugly. So the denominator right here is 1/4. So what we can do is do a clever trick. If I multiply this one by 4/1, those will cancel. Remember, we've talked a lot about canceling and undoing, canceling to be 0, canceling to be 1, and that sort of thing. So if I multiply this bottom one by 4, the 4's will cancel, I'll be left with a 1. And if I do the same thing on the top, here's what I'm left with. On the bottom, those are going to cancel, I'm left with a 1, and on the top I'm left with 2/3 times 4/1. And that would just be the answer right there. I've successfully changed a division problem into a multiplication problem. Well, this is the long way of doing things. We'd hate to do this every single time. So instead what we do is we say, well, look, if this is just going to turn into this every single time, let's just take this and let's kind of cut out the middle part and just say, okay, we're just going to flip that over and we're going to multiply. We're going to multiply by the reciprocal. So if I had something like this, let's say I had 5/7 and I was dividing by 1, let's do something more interesting. Let's do 10/9. Well, then we change this to 5/7 times 9/10. If there's any cross canceling that we can do, we would do that. So we end up with 1/7 times 9/2. So I end up with a 9 on the top and a 14 on the bottom. We could go through the same process of writing it like this and multiplying the top and bottom by the same number, but that's basically why we do it, is we're basically making that denominator so that it's just a nice number like a 1 there. So that's it.